Hi everyone, welcome back to part 2 of maximums, minimums and the second derivative test. I've tidied up that diagram that we were drawing before, but the idea of the diagram is still the same. Observe that for the function y of x, y prime of x is decreasing along this blue interval here. Y prime of x is decreasing right up till that point because the tangent lines, they start out steep and then they get less and less steep as we go along until finally the slope of the tangent line is 0 at the point x1, and then it becomes negative, and then it gets more and more negative right up till about that point there, and then once we get to this point here, all of a sudden they start to get less negative, so they start coming back around again until finally they get back to 0 at the point x2, and then they'll keep increasing, getting more and more positive up until about this point, up until about here, and then they'll start to get kind of more less positive until they reach 0 at this point again. So we can get an idea of what the function y prime of x looks like just by looking at the tangent lines on this graph. So it's decreasing. It reaches 0 here. It's decreasing all the way to this point. Then that's the most negative it becomes. We better give that point a name, actually. So let's call this point x3. And then it's kind of increasing until it becomes the most positive it can become along this interval. And so this point we'll say is x4. And so if we draw this as a graph, if we draw the graph of y prime of x, it looks something like this. I told you we'd come back to this graph. And this is where y prime of x equals 0. So that has to be on top of the first hill because it's decreasing all the way to that point. And so this point must be, wait, what did I call that point again? Yeah, x1. So this point must be x1. Oops. This point must be x1. Similarly, when it's 0 again, that must be when it's at the bottom of that hill. So this point is x2. And this point here was when it was the most negative it could possibly become. So that must be x3, because if we go back to the graph, we see that right here is where the tangent lines are the most negative they can be in this area. So that one is x3. And then x4 is where they're kind of the most positive they can be before the slopes start becoming less and less steep. So this point here must be x4. This point must be x4. All right, let's go back to the diagram. Let's go back to the diagram again because there's a couple of other details we should pay attention to. So first of all, if we draw a circle around x1, so I'm going to draw a pink circle around x1, and this is the same circle. This is the same circle. So inside that circle, the function looks like this with x1 at the top. Well, because inside that circle, there is no other value of y of x that is bigger than y of x1, we say that x1 is a local maximum. Now, it's not a global maximum. It's not an absolute maximum because, for example, this point here is bigger than y of x1. That point there is a bigger value. So it's not a global maximum of the whole function. It's just a local maximum because I can draw a circle around it such that it's the biggest value in that circle. So that makes it a local maximum. Okay, and we can see from this that suppose the tangent line slopes are decreasing and then they reach 0. So suppose y prime of x decreasing around a point x1, and so suppose y prime of x is decreasing around x1 and y prime of x1 equals 0. Well, that means that the graph must take this kind of shape. because the slopes are decreasing and it's equal to 0 at x1, we must have that kind of shape that we have in the circle there. So it must be the case, that x1 is a local maximum. x1 is a local maximum. It must be the case. So if y prime of x is decreasing around x1 and y prime of x1 equals 0, then x1 is a local maximum. Another way to write this, well, we can see that, well, going to our graph of y prime of x, we have that y prime prime, so the slope of this tangent line is y prime prime of x1, that is less than 0. If y prime prime of x1 is less than 0, that means the tangent line slopes are decreasing around x1. And don't forget y prime of x1 equals 0. So if this is the case, if y prime of x1 equals 0 and if y prime prime of x1 is smaller than 0, now y prime prime of x1 means we differentiate y prime of x again. So we differentiated y of x to get y prime of x, so that gives us another function of x, and we can differentiate that one again, supposing the function is differentiable, which it is in this case. So if we differentiate y prime of x, we get y prime prime of x. Now in this situation where y prime of x1 equals 0 and y prime prime of x1 is less than 0, this must mean that x1 is a local maximum. This must mean that x1 is a local maximum, because y prime of x1 equals 0 tells us that the tangent line is flat at the point x1 on the graph of y of x, and then y prime prime of x1 less than 0 tells us that those tangent line slopes are decreasing. Sorry, that's the wrong place to draw them. Tells us that those tangent line slopes are decreasing around x1, getting less and less positive until they reach 0, then they start becoming more and more negative. Well, that must mean that we have a kind of a upwards hill until we reach x1 at the top. And that means that x1 is a local maximum. Okay, we can do a similar kind of thing with x2. Draw it on another board. So at our point x2, if we draw the circle around x2, inside the circle our function looked like this. And here's x2 at the bottom there. x2. Okay, so x2, the tangent lines are actually getting less and less negative. So first they're negative, then they're getting less and less negative, and then finally it reaches 0 at x2, and then they start to get more and more positive. So actually the tangent line slopes are increasing around x2. So that tells us that y prime of x is increasing around x2. So conversely, if y prime of x is increasing around x2, then we must have that x2 is a minimum, assuming y prime of x2 equals 0, of course. So supposing y prime of x2 equals 0 and y prime of x is increasing around x2, then it must mean the tangent lines are behaving in this way. And so we must have that our function does take this kind of shape with x2 at the bottom of that little hill if we draw a small enough circle around x2. And so that must mean that x2 is a local minimum. Now, if y prime of x is increasing around x2, another way to write that is y prime prime of x2 is bigger than 0. That's another way to write that. And if we go to our graph, we can see that that's the case. So y prime prime of x2, if I draw the tangent line, so this is the slope of this tangent line is the derivative of y prime of x. Remember, this is the graph of y prime of x. So the slope of this tangent line is the derivative of y prime of x at the point x2. So slope is y prime prime of x2. And we can see that this is bigger than 0. So supposing that y prime of x2 equals 0, and if y prime prime of x2 is bigger than 0, then that means that y prime of x is increasing around x2 until it reaches 0 at x2, and then it starts getting more and more positive. So it can only, if it's 0, if the slopes of the tangent lines are 0 at x2, it can only mean that if y prime of x is increasing around x2, it can only mean that first the tangent lines are getting less and less negative, and then finally they reach 0, then they start getting more and more positive. So the function must have that kind of shape. It must have that kind of shape. And so x2 must be a local minimum at the bottom of that little valley. All right, let's collect what we just discovered there. So if y prime of x1 equals 0 and y prime prime of x1 is less than 0, then it must be that x1 is a local maximum. It must be that x1 is a local maximum. If y prime of x2 is equal to 0 and y prime prime of x2 is bigger than 0, then x2 is a local minimum. Then x2 is a local minimum. So if these conditions are true, then we can tell whether the point is a local maximum or a local minimum. If y prime prime of either of them equals 0, then we get no information. We get no further information about it. This is called the second derivative test. This is called the second derivative test. Okay, this is kind of important. This is a very important detail. If y prime of x1 equals 0, so if this is true and this is true, then we know this part here. Then we know this part here. If those two conditions are true, then we know the second part. However, if x1 is a local minimum of a function, it's not necessarily the case that y prime of x1 equals 0 and y prime prime of x1 is less than 0. It's not necessarily the case. This theorem only goes one way. What I mean by that is if we know this part and we know this part, then we know the second part. We know that x1 is a local maximum. So if we know the first part and we know the second part, then we know that x1 is a local maximum. However, knowing that x1 is a local maximum doesn't necessarily mean that y prime of x1 equals 0 and y prime prime of x1 is less than 0. Let me give you an example. So I'm going to draw 3 graphs on here. So this is the x-axis, this is the y-axis. The first graph I'm going to draw is y of x equals x to the power of 4. Oops. Looks like this. So you can plot this if you don't believe me. Kind of looks like x squared, except it's much flatter in the middle once you get past 1. Because taking a smaller number between 0 and 1 to the power of 4 makes it much smaller than if you square it. Okay, so this is y of x equals x to the power of 4. I may as well call it y1 of x. This is y1 of x equals x to the power of 4. And then I'm going to draw another function, which is actually just going to be the negative version of this. This is y2 of x equals negative x to the power of 4. Equals negative x to the power of 4. Well, we can see that the point 0 for both of these functions, well, y1 prime of 0 equals y1 prime of 0, and that's just, they're both equal to 0, even though 0 is a local minimum of y1 of x. 0, a local min of y1 of x. 0 is a local minimum of y1 of x. But still, we don't have y1 of 0 equals 0 and y1 prime of 0 bigger than 0. We don't have that. So if we go back to the information we collected, we don't have that x2 is a local minimum shows that y prime of x2 equals 0 and y prime of x2 is bigger than 0. That doesn't have to be the case. It's only if we know that y prime of x2 equals 0 and y prime of x2 is bigger than 0, then we know x2 is a local minimum. Knowing something about x2 doesn't really tell us that much about the derivatives, actually. It doesn't really tell us that much about the second derivative. So y prime of x2 doesn't have to be bigger than 0 just because x2 is a local minimum. That's very important. Similarly, 0 is a local maximum. 0 is a local maximum of y2 of x. But still, y2 prime of 0 equals y2 prime of 0, which is equal to 0. So we don't have that y2 prime of 0 is bigger than 0. Very important. There's one more graph that we should draw, actually. There's one more graph that we should draw. Just to get a point across here. And actually, just because y1 of 0, just because y prime of a point and y prime of a point equals 0, that doesn't mean the point has to be a maximum or a minimum even. Let me show you what I mean. This is the function, if you haven't already seen it, this is the function y of x equals x cubed. Y of x equals x cubed. You'll find it looks like this. We're going down in the negative direction because when you take a negative number cubed, you still get a negative number. Excuse me. When you take a negative number cubed, you still get a negative number. And so this point here, this point 0, well, y prime of 0 is equal to 3 times 0 squared, which is equal to 0. Better do some calculations here, just so you know what the heck I'm talking about. Y prime of x is equal to 3x squared, and therefore y prime of x, we differentiate it again, you're going to get 2 times 3 times x, so 6x. So y prime of 0 is equal to 3 times 0 squared, which is equal to 0, and also y prime of 0 is equal to 6 times 0, which is equal to 0 again. Even though 0 not a maximum and 0 not a minimum. So 0 is neither a maximum nor a minimum, but the first derivative of y at that point is equal to 0, and the second derivative of y at that point is equal to 0. And so 0 is not a maximum or a minimum. We call such a point, I believe, such a point is called a point of inflection. Point of inflection. Right, so in summary, we know that if y prime of x1 equals 0 and y prime of x1 is less than 0, then it must be the case that x1 is a local maximum. We also know that if y prime of x2 equals 0 and y prime prime of x2 is bigger than 0, then x2 is a local minimum. And this is called the second derivative test. And knowing anything else about if we don't know these two facts about the derivatives, then actually we don't know anything. It could be a maximum, minimum, or a point of inflection. Okay, thanks very much for watching. Don't forget to check out the notes on this topic and do the exercises at the back. See you guys next time. Take care. Bye.